Now we are going to look at some parametric equations that are a little bit more complicated. As you notice in the first one, we have some fun trig functions that are in our parametric equations. So notice that we have a theta variable in there instead of a t. So what we want to remember to do is plug in radian measures to our parametric equations. So theta must always be in between 0 and 2 pi. So these are the values that we are going to plug into our table. So instead of having t, x, and y, we're going to have theta, x, and y. The values that we want to plug in for theta are the same values that we use in our unit circle. So let's remember what those values are. So we have 0 over here and 2 pi, pi over 2 up here, pi, and 3 pi over 2. Now let's write down what the coordinates are at those trig values so we can easily take the sine and cosine of these angle measures, since that's what we're going to have to do when we fill out our table. So we know that the coordinate at 0 is 1, 0. The coordinate at pi over 2 is 0, 1. The coordinate at pi is -1, 0. And the coordinate at 3 pi over 2 is 0, -1. All right, so the values that we're going to plug into our table for theta are 0, pi over 2, pi, 3 pi over 2, and then finishing with 2 pi. All right, so if I take 0 and plug it into x equals cosine theta, remember that the cosine of our angle measures is always the x value. So the cosine of 0 will equal 1. The cosine of pi over 2 is 0. Cosine of pi is -1. The cosine of 3 pi over 2 is 0. And then at 2 pi, we're back to 1. And the sine of all of our angle measures is the y value. So 3 times the sine of 0 is 0, so just get a 0 there. The sine of pi over 2 is 1, so times 3, we have a 3. The sine of pi is 0, so we're back to 0. The sine of 3 pi over 2, we are back to -3. And the sine of 2 pi is 0, so we are back to 0. So let's go ahead and put these coordinates on the graph. And remember, we're only graphing x and y. I am making this problem very beautiful, I think. Good colors. Oh, which one haven't I used yet? Oh, put in some more green. Okay, so we have a point at 1, 0. We have a point at 0, 3. Point at -1, 0. 0, -3. Oops, I'm going to erase that. Don't want any weird lines going on. Okay, and then back to 1, 0. So, as you can see, we have an ellipse. Ooh, see how this is all connected now? All right, but with all parametric equations, we have to put the arrows on our graph. So, as our x's are getting bigger, well, our x's are kind of traveling around in the circle. So how we want to do this is just kind of follow along the y values. So we started at 0, we went up to 3, so our arrow is going to be going this way. And then we went back down to 0, down to -3, and then back up to 0. So that's the way that our arrows move for this particular ellipse. So now what we need to do is write these parametric equations as one rectangular equation. The problem is we cannot get theta by itself the same way that we got t isolated in the last problems. However, we can use a Pythagorean identity to help us out. And that Pythagorean identity is cosine squared theta plus sine squared theta equals 1. We know that cosine squared theta, well, we know that cosine theta in this case equals x. So we can plug an x in for cosine and then just square that. And if we isolate sine by dividing by 3, we get that sine is y over 3, and then we just square that. So the final equation for this ellipse would be x squared plus y squared over 9 equals 1. And if I take a 1 and write it underneath that x squared, you can see that this is the standard form of an equation of an ellipse. Let's take a look at these next two parametric equations. We have x equals e to the 2t and y equals e to the t. So we're back to plugging in values for t. So what we need to recognize is, are there any restrictions for t? And in this case, there's not, because we can raise e to any power that we want to. So let's make a table, t, x, and y, and we'll just plug in some basic values for t, -2, -1, 0, 1, and 2. So if I plug a -2 in to the first equation, the x equation, I get e to the -4th, which is, using my calculator, 0.02. E to the -2nd, if I plug a -1 in there. We get 0.14. E to the 0 power is just 1. E to the 2nd, 7.39, and e to the 4th is 54.6. Okay, now let's take these t values and plug them in to the y equation. So if I take a -2 and plug it in, e to the -2nd, oh, we already got that value from when we plugged a -1 into the first equation. So we know that that will be 0.14. We don't know what e to the -1 is yet, so let's plug that in. We get 0.37. E to the 0, of course, 1. E to the first, we know that that is 2.718, or 2.72 if we round. And e to the second, we know that from last time, is 7.39. Okay, so this graph that we're going to create is going to have a lot of decimals in it, but that's okay. We'll just graph it as accurately as possible. This graph has to go all the way to 54, and it doesn't look like our x values go below 0, so I am going to redraw this graph. like this. All right, start plotting our points. So we have a point at 0.02, 0.14, so that's going to be extremely close to 0. 0.14, 0.37, again, extremely close to 0. 1, 1, there we go, point we can actually graph. 7.39 and 2.72. So about right there. And then this graph is going to shoot off towards 54,7.39. So upon looking at this graph, it looks like that we have a square root function, since square root functions are typically graphed like that. But let's turn this into a rectangular equation and see what the final outcome is. So again, we want to isolate t in the x equation. So in order to do that, we need to take the natural log of both sides. So the natural log of x equals 2t. So t equals 1/2 of the natural log of x. So now we're going to take that and plug it in for the y equation. So y equals e to the 1/2 natural log of x. And we notice that we have an e with a natural log in the exponent, and we want to cancel those out. But remember, we're not allowed to cancel them out until we take this 1/2 and move him to the exponent. So y equals e to the natural log of x to the 1/2. So y equals x to the 1/2, which is the same as the square root of x. And so now we see that indeed it does match up with the square root function. So we still need to recognize our restrictions for x and y. And remember, we have no restrictions for t. As you can see, our x's get very close to 0, but they don't go below it. So we know that x is greater than or equal to 0. And the same for y. And if we look at our initial equations, that makes sense, because no matter what power we raise e to, we'll never get a negative number or the number 0. So actually, x is strictly greater than 0 and y is strictly greater than 0.